Hi everyone. Today we're going to start on 4.3, which is called partial derivatives. So we're actually going to take a break from talking about like different type of functions and what they represent, but instead talk a little bit about calculus for a little bit. So partial derivative. What does it mean by partial derivative? So partial derivative is actually relating to a function that have several independent variable. So let's start with the following. Let's start with the definition. Let's say given a function f that map from Rn to R. Now, before we go any further, the first question I want to ask is, do you remember what does this function represent? A function map from Rn to R? And yes, it represents a n-dimensional surface in Rn plus 1. Now, let's say we have a function f that map from Rn to R with, let's say, vector x being the input, which is x1, x2, to xn. And I guess I can call the output y. Okay, so this function f of vector x would equal to y. We're going to define something called partial derivative. Now, important to understand, it's called a partial derivative because it is not a derivative. The term partial indicates that it's only part of something. Okay, so therefore we're not defining a derivative of this function f, but rather define something that's part of the derivative of function f. So the partial derivative of the function f with respect to let's say one of its independent variable, x sub k. Notice no arrows on top because that refers to one of the number inside here, the cave numbers, is defined to be the following. So here's the formula. Limit as h approaches 0, f of x1, x2, to x sub k plus h, to xn minus f of x sub 1, x sub 2, to x sub k, to x sub n over h. Now, some of you might recognize this expression because this looks strangely like the definition of the derivative, except that the definition of derivative has only one independent variable, but here we have n independent variable. However, notice the similarity is that only one of the variable has that plus h attached to it. Okay? Now, I'll explain further of what it is, but let's give you the correct notation first. This is actually defined to be the following. It's defined to be df over dx sub k. Now notice that the d that I wrote is a little weird. It is a scripted d for partial derivative. So therefore it's not the same as just regular d over df over dx sub k. Okay, this is a scripted d for partial derivative. So whenever I use this scripted d, that implies partial derivative, which is not the same, not to confuse with just regular d. Okay, so notation wise, it's not df over dx sub k. Okay, that's not the same. This is a scripted d that indicate partial derivative. And as a matter of fact, that's how we indicate partial derivative, by using the scripted d. So what is a partial derivative? So a partial derivative is basically a ratio between the change of the dependent variable, in this case y, versus the change of one of the independent variable. So only one of the independent variables. Here's the kicker, here's the important part, while all the remaining independent variable are fixed, meaning they remain constant. While all the rest of the independent variables remains constants. So therefore, a partial derivative simply look at how one independent variable changes the dependent variable. Okay, and the only independent variable that we're looking at is basically x sub k. Okay. Now, before we actually get to how to do it, maybe give you some simple example to illustrate and show you how the notation work first. Okay, so that way you can understand how this notation is. So example, suppose we have a function f that maps from R2 to R. So of course I have to ask this question, what does this function f represent graphically? Okay, so if you want to take a minute to think about it, pause the video and think. Okay, it's important. I'm going to ask this question every time, almost every time I'm going to put a function down. So function f that maps from R2 to R, it represents a two-dimensional surface. So if you just say surface, you're okay, because we refer to a surface as a two-dimensional surface. A two-dimensional surface in R3. Suppose we let z equal to f of xy. Then here's something important to write down for yourself, because this function has two independent variables, x and y, therefore result in this function having two partial derivatives. So what are these two partial derivatives? These two partial derivatives can be called df over dx, notice the script of d, and df over dy. So one partial with respect to the first independent variable, which is x. The second one with respect to the second independent variable, that's y. Because I also let this function, the output, to be z, this can also be referred to as dz over dx or dz over dy. And they're defined by the following limits. This one is defined by limits h approaches 0, f of x plus hy minus f of xy over h. Notice the x get the plus h because it is a partial derivative with respect to x. So now for this one, which is a partial derivative with respect to y, we're going to say limit x approaches 0, f of xy plus h minus f of xy over h. So one of them changes the x slightly and try to figure out what the limit would be, and one changes the y slightly and try to figure out what it happened to be. And if you change x, you have the partial derivative with respect to x. If you change y, you have the partial derivative of y. Now here's something interesting. So there is a second notation that we use for partial derivative, and it is a little bit cleaner, I would say, but also less intuitive. Because if you look at this expression right here and this expression right here, you kind of know that you're dealing with derivative, because that's the kind of notation that you have been using in BC calculus, except that you use a regular d instead of using this like little scripted d. And yes, that scripted d look kind of like the number 2 or the number 2, which is perfectly okay. That's how I draw it. So you can probably draw something similar too. Okay. However, there is a second notation that describe partial derivative, and this is called subscript notation. For partial derivative. Okay, and that notation is this. We'll call this f sub x, or sometimes called z sub x. Depending on whether you want to use the function name or the dependent variable name. And so what is this one right here, which is df over dy or dz over dy? It will be f sub y or z sub y. you will see both notation being used, so therefore make sure you understand both of them. I personally like the dz over dx or dy over dx, and I'll explain to you why that is the case in a little bit. But subscript notation definitely nice because less writing. And also one of the key thing about it is that using this notation does clean up your work a little bit because of the less writing, and also how the notation work. And I'll explain to you how that why that's useful as we get move along in this section. Okay. So maybe we can try an example together before I show you more. Okay, so how about we try this example right here. Now here's the interesting thing. Obviously, as you probably expect from last year in BC Calculus, yes, you learned the definition of the derivative, but when it comes to finding the derivative, you actually don't use that definition at all. Okay, because why? The definition is complicated to use. You want something nice and simple to find the derivative so that you can actually move on with the rest of the problem. So here with partial derivative is the same exact idea. So I'm going to show you how to actually form partial derivative, and we are actually not using the definition, even though that is how it's defined, but we're going to be using a very simple way to find partial derivative. Okay, so show you. Suppose we have this function right here. I'm going to have let's say we let f of xy equal to x squared plus 2xy plus 5y to the third. Okay, and what I'm going to ask you to do is the following. How about let's find the two partial derivative. Okay, and then how about B? Let's evaluate them so that you know how does that work. At I don't know, 1, 2. How's that? Okay. So show you how to find the derivative. So let's do part A. To find df over dx, what I basically do is I'm going to take the partial derivative, d over dx, that's called differentiating. So that is the process of finding the derivative of something. So I'm going to take the derivative of f, which is x squared plus 2xy plus 5y to the third. Now here's something very important that I want to point out. In here, when I differentiate this, it's different than something that you might remember learning last year called implicit differentiation. This is different than implicit differentiation. In what way? In implicit differentiation, when you differentiate a function, an equation involves both x and y, what you want to do is to imply y is a function of x, meaning that you're implying that y is a dependent variable, with x being its independent variable. But here is not the case. In here, we are defining a function in both x and y together, meaning that both x and y are independent variables. And the fact that they're independent variable tell me that x and y are independent of each other, hence the name independence variable. So how does that change the way we find the derivative? This is how. When finding partial derivative, with respect to one independent variable, we will do this. We will treat all other independent variables as constant. So therefore, they are actually, we think of all other independent variables as constant. Now, here's something important that I want to point out. So therefore, when you try to find partial derivative, it's extremely important that you pay attention to what variables are independent and what variables are dependent. Why? because we will be doing implicit differentiation later in chapter 6. So if you don't learn to solve things out like right now, you're going to get all confused by the time we get there. So in here, because the function is defined to be f of xy, both x and y are independent. And therefore, when I form this derivative, this is what will happen. Partial derivative works exactly the same way as regular derivative. When I differentiate a whole bunch of things add together, I'm going to separate them. And now I can differentiate each one individually. Notice when I differentiate x squared with respect to x, that just becomes 2x. Now, here's the important one that students often make mistake. When you differentiate 2xy with dx, here's the important part. 2 is a constant, so obviously we can move out the 2 from the differentiation. But y is also a constant because y is what other independent variables are. And therefore, that is also constant. Oops. And therefore, I'm actually differentiating just x with 2y being the constant that get pulled out from the partial differentiation. So that just becomes 2y times 1. Plus, what happened to differentiating 5y cubed with dx? 5 is a constant. Y is also considered a constant. So therefore, this whole term just becomes a constant. That derivative becomes 0. So notice it's very different compared to partial derivative. In partial derivative, you're treating x and y both as variable. But in here, in a partial derivative with respect to x, x is the only variable. Why? Because the other independent variables is considered to be constant instead. So therefore, what is the partial derivative with respect to x? df over dx is equal to 2x plus 2y. Now I can definitely do the other one, df over dy. So that will be d over dy of x squared plus 2xy plus 5y to the third. So once again, I basically differentiate each one individually. So therefore, I'm just basically taking the derivative with respect to y of x squared plus the derivative with respect to y of 2xy plus the derivative with respect to y of 5y to the third. So what is the derivative of x squared with respect to y? Because it's partial derivative, x considered to be constant when I differentiate with respect to y. So derivative of constant, 0. Plus, what happened to the derivative of 2xy when we differentiate with respect to y? Same thing happened as on this side. The 2x is now a constant. As we differentiating y, which have a derivative of 1. So therefore it becomes 2x times 1. Plus, what's the derivative of 5y to the third with respect to y? That would be 15y squared. So therefore, this gives me df over dy, which is equal to 2x plus 15y squared. So when you're taking a partial derivative, remember you are only differentiating against one variable that's indicated on the bottom of your differentiation symbol. And that one variable is a constant. Any other independent variables are considered to be this one independent variable that you differentiate with respect to is the only variables. Any other independent variables, they are considered to be constant in the differentiation, and therefore is no different than like the number 5 or the number pi or any numbers that you know. So important to keep that in mind, and we'll do more examples so that you can see how that works. So now I can evaluate both of these. Okay, so therefore, essentially, when I take the differentiation process, we generate these two partial derivatives, but they're actually more accurately referred to as partial derivative function, because they're both functions. And now I can evaluate them. So when I evaluate them, I can evaluate them at 1, 2. And therefore just simply require me to plug in 1 for x and 2 for y. So therefore this come out to be 6. And this one, yeah, let's write here. So it'll be 2 plus 60, so 62. Okay. Now what happens if we have 3? A function that map from R3 to R1. So well, let's take a minute to think. Okay. What happens if now we have, let's say we have a function f that map from R3 to R1. What does this function represent? Yes, it's the same question that I just asked before. What does this function represent? This function represents a 3-dimensional surface. No, it is not a solid. Remember, only solid exists in a dimensional space is the same dimension as the space is in. So because this particular function is in R4, unless we talk about 4-dimensional object, then we'll refer to it as a solid in R4. Otherwise, it's all surfaces unless it's 1-dimensional, which we call that a curve. Okay, so this represents a 3-dimensional surface in R4, and the 3-dimensional surface does not behave like a solid when it's in R4. It behaves like a surface in R4. All right. So what are the partial derivatives that we could have in this case? So in this case, this function, I'm going to go and call this function w equal to f of x, y, z. And so therefore, it has 3 partial derivatives. How do I know there are 3 partial derivatives? Because it's 1 for each of the independent variable. In this case, the 3 partial derivatives df over dx, df over dy, and df over dz. And remember, use a scripted d, because otherwise I will have to mark it incorrect. Okay, because you have to indicate that the derivative is partial versus single variable derivative. Those are different things. Okay, so these are 3 partial derivatives. So let's see if we can find them. So let's just try to find them. So let's say we go let f of x, y, z equal to x squared y plus y squared z plus let's say z squared x, I guess, or xz squared. How's that? Okay. I'm going to ask you to go ahead and find its 3 partial derivatives. Okay? So hopefully it shouldn't be too hard for you to do once you understand the concept of treating only one variable as one independent variable as the variable that you're differentiating, while treating all other independent variable as constant. It's actually very easy to do. As a matter of fact, it really helps in the sense that when you do this, you run into less product rule, less chain rule, less quotient rule because of that. Okay, unlike last year in implicit differentiation, you run into those 3 rules all the time. So let's go and try this one. So if you want to do that first before I show you the answer, you should definitely do that. Just pause the video and do that. And then once you're done, you unpause and watch the answers. So I'm going to go and do the problem. df over dx would be when you differentiate with respect to x of x squared y plus y squared z plus xz squared. So x squared y, remember y is a constant, so that stay. And we just simply differentiate x squared, which is 2x, so it becomes 2xy, plus y squared z. None of them are variable, because the only variable is x. Y and z are considered to be constant in this case, so therefore this is a whole constant. So derivative will be 0, plus x z squared. Z squared is a constant, so therefore that falls out of the differentiation. X is the variable. When I differentiate, it becomes 1. So it becomes z squared times 1. So therefore, it becomes 2xy plus z squared. All right, let's do the other one. df over dy. So therefore, it's d over dy of x squared y plus y squared z plus xz squared. So x squared y, when I differentiate the x squared stay, and I just differentiate y, which is 1, so it become x squared times 1, plus y squared z stay, because z is a constant, so I differentiate y squared, which is 2y, so it become 2yz, plus xz squared has no y involved. That means the entire thing is a constant. That gives a 0 derivative. So it become x squared plus 2yz. df over dz. So that would be d over dz of x squared y plus y squared z plus xz squared. So x squared y have no z in it, therefore its derivative is 0, plus y squared is a constant, derivative of z is 1, so it becomes y squared times 1, plus xz squared. The derivative of that is x times the derivative of z squared, which is 2z, so it becomes 2xz. So therefore this becomes y squared plus 2xz. Alright, so now one last thing I want to talk to you about, and that would be all that I want to talk about for today. So hopefully we can end before 30 minutes mark. So here, if you look at what we have seen so far with these two examples, notice the following. In our first example, we have a function f that maps from R2 to R. Notice that the derivative, the partial derivative, df over dx and df over dy, both of them, if you look, both of them are also in terms of x and y, and they also give a one single number as an outcome. Therefore, notice that df over dx and df over dy are also both R2 to R. Now, more interestingly, if you look at our second example, which maps from R3 to R, df over dx, df over dy, df over dz, all three of them involve x, y, z, and they actually all give us one single numbers. So notice this pattern. Remember that forming pattern is a very powerful tool in learning math, and therefore implies the following. If f maps from Rn to R, then its partial derivative, no matter which one it is, let's say df over dx sub k, is also from Rn to R, and therefore implying that partial derivative, the process of partial derivatives, or actually maybe I should probably say better, partial differentiation, because derivative is the outcome, but the process that we do is called differentiation. Partial differentiation actually has closure, and therefore it actually allows us to repeatedly differentiate or partially differentiate a function. Partially differentiate a function. So what happened when I partially differentiate a function repeatedly? What do I get? Well, we get what we call higher order derivative, which would probably be for tomorrow's video than today's video. Alright, so I think that's it for today. So I will talk to you in either tomorrow in class or in tomorrow's video or next video. Alright, talk to you guys later. Bye bye.